We have Philippe. We're finishing his first year of PhD in the same group, but doing very different things, as you will see. So, Philippe, thank you very much.
Thank you for having me. So, I will be presenting to you I will be presenting some results on the experimental results, at least on nonlinear waves along a torus of fluid. So, how does a torus of fluid actually look like? Well, it looks like this. So here we have a plate that's actually a super hydrophobic plate. And I actually bought a pocket version that if someone wants to check later and see how it actually works, feel free to ask. So the basics of it, the plate is super hydrophobic. It has a contact angle with water of around 160 degrees, which is pretty large. And there's a very small groove running along the perimeter, which is actually symmetric with the center, that basically prevents the water from closing in, because tori are essentially unstable under capillarity, but it is this slight slope here that prevents it from actually closing in. So the setup looks more or less like this. So as I said, there's this groove that's around 4 degrees, which is very small. And essentially, first, what we were interested in was actually simply studying the linear waves that can propagate on the torus. And essentially, we focus on azimuthal waves that propagate both on the exterior, but also on the interior of the torus. We do so by conducting a frequency sweep, and simply we were very interested just looking at the the Fourier spectrum and what does it give, what are the dispersion relations, and simply because it is not at all clear what would happen. So once you do this, so we take a video, we get the measurements of our displacements of the borders, and we find we look at the Fourier spectrum from both the inner and outer borders. So we can see that this gives a actually surprisingly rich structure in terms of dispersion relations. So primarily, if we focus on the outer borders here, we starting from 0, we have what we can identify as gravity capillary waves. But moving up, we have very different branches that start to appear. And also on the inner border, for example, we do not see the gravity capillary branch to be as present, but we see the second one appearing that is much stronger than here. So sort of to start to get a more complete picture, we superimpose the two and we try to model these both using results that were already known in the straight case of waves propagating along canals, and trying to apply it to the case of the torus, which is not at all trivial because we have the geometry of the canal, we have the additional curvature coming, we have the curvature that is both colloidal and radial. In terms of analytics, it's not really possible to get the results. Already in canal cases, it's difficult to model when the canal starts being a triangular shape. But here, nevertheless, we managed to find a relation that describes pretty well gravity capillary waves to start with. We see the appearance of actually the gravity to be changed because since the waves are moving along the slope of the groove, they actually experience only the projection of the gravity onto the slope. So instead of experiencing 9.8 meter per second square, they experience 0.8 essentially. So this is a huge reaction in the gravity of the gravity regime. We also see additional capillarity for high wave numbers. And we start to consider the above branch, the additional branches that we observed. Well, first we see that this one, the marked S here, is completely different than these ones because asymptotically here at high K, it has a different behavior. And this actually corresponds, as I will show you, to the movement of the center of mass of the cross section of the torus within the canal. And the additional modes here actually correspond to something called sloshing modes, which also have a sort of a coupling, but it's still linear with the transverse mode across the torus. So, but to better visualize this, we can look at the cross sections. So the center of mass wave includes the movement of the center of mass, and so it's propagating like this in the azimuthal direction. but the center of mass is moving like this, up and down along the slope. And we can actually, this frequency, so the cutoff frequency that you saw here, corresponds actually exactly to the frequency that we would get like with the classical result of just looking at a ball that's oscillating in between two slopes. Then we have the sloshing waves. These do not move the center of mass, so it stays put. But we have an azimuthal wave that has this transverse sort of mode appearing. So since we can have multiple modes appearing, we have multiple branches appearing, each of which corresponds to a different transverse mode. So this has been the linear case. It provided some rich structure, which we managed to explain, but this has been very low forcing. So when we try to force the torus more, so in the next step, what we decide to do is to force it with an impulsionally. So we just push it a bit, and it generates actually these two structures that we see here, counter-propagating around the torus. And we were wondering if this could actually be some sort of solitons. Since the impulsion is pretty strong, it could provide something nonlinear. It's also a good guess because the main dispersion relation is shallow water gravitocapillary waves, which have been known to produce Korteweg-de Vries solitons actually. And just to mention, we will be considering two sizes of plates, one large, one small. Just keep that in mind for later because it will be important. So are these solitons or not? This is the first question we can ask. Well, if we take already just the Fourier spectra of single solitons propagating around the torus, we see that it's essentially this without dispersion, which is a good indication for Korteweg-de Vries solitons, because solitons essentially what they do, they balance dispersion, which tries to elongate them, with nonlinearity that tries to sort of narrow them. And essentially this leads to a structure that propagates without any change in width or in wavelength, which corresponds to a non-dispersionless structure. In addition, we can also see they're actually subsonic in terms of the phase velocity of gravity waves. This appears also in the Korteweg-de Vries case for gravity capillary solitons. So we're on a good track here. Also, we can look at the interaction of the solitons to see if they are really interacting nonlinearly, or are they just passing to each other. And indeed, if you look at this interaction here, and we and we consider only the propagation of the peaks of each soliton in time, we see that at the moment of collision, there is a relatively long residence time. And if you actually look at the video a bit more, you will see the solitons coming in, staying, and then leaving. And there is a small dephasing between what happens of a soliton before and after the collision. Again, very good indications of solitons. And now what we want to do is try to model this. So we take a dispersion, gravitocapillary dispersion relation. We manage to, by taking appropriate expansions around the small wave numbers, we manage to find the dispersion part of the KVV. And also from input, using input from also the straight line case, and what we know of the dispersion relation, we managed also to find a nonlinearity that describes pretty well what's going on. And it's pretty well known, so in Korteweg-de Vries equation, we can solve this, and this yields a solitary wave solution, which is a hyperbolic second. So which we, when fitting to data, here describes it pretty well. So there is no fitting parameter here. You may ask, why is this negative and why is the amplitude negative? Well, I'll come to that, but it has to do with the dispersion term here. One more prediction coming from Korteweg-de Vries theory is that the velocity of the solitons will depend on the amplitude. So as the bigger the soliton, the faster it goes. And this dependence is linear, and we can verify also this as well. So this is the data here with the prediction given by the Korteweg-de Vries equation, and it described it pretty well. So far so good. We also may ask, so as I said, amplitudes can be negative. They can also be positive of the solitons. So it can be either a bump that's propagating or a hole that's propagating. And this has to do with the dispersion relation and with the dispersive term in the KdV equation. As it turns out in the torus, this also starts to depend on curvature. So in the straight case, this will depend simply on the ratio of gravity with respect to capillarity. It's similar here. We have this capillary term here, so the capillary length that's coming in, and also the size of the torus. But we have this additional sort of curvature term that's coming in and starting to affect our dispersion. And so depending on the dispersion relation shown here for 3 different sizes of the torus, we can either have the Persian solitons for the red dispersion relation, which is completely convex, or as we increase the size of the torus, it's the near 0, we start changing the shape of the curve, and we start to have elevation solitons. And this we can actually predict at what torus size will the solitons change from negative to positive amplitude. And actually, there is this sort of analysis gives a good prediction, and we managed to verify this. But there's an issue. In fact, so as I mentioned, we take a large plate, everything's well, everything works fine, KdV results hold well. But if we take the small plate now, and we do the same sort of procedure, and we start measuring the soliton velocities, we start to get all of these points here, which shouldn't be there. And what's going on actually is the best way we saw to explain this, and actually is pure results can still be described completely by KdV, but we simply neglected the fact that we are actually in a periodic domain. So what is going on? We will consider a more general solution of the KdV equation, knoidal solutions, which, so this is the Jacobic knoidal function. It has the elliptic parameter m here, which for m equals 1 gives our well-known soliton solution, the hyperbolic second. For m equals 0, this is a simple cosine, and in between we have a whole spectrum of the sort of nonlinear waves, which is governed by this m here. But as I said, we are in a periodic domain. We need to wrap this on a circle. And what this does is simply imposes a boundary, so simply imposes a condition on the delta here. So much like if we try to fit the cosine, we would only get single modes, 1, 2, 3, 4. It's the same here, but the periodicity condition, it turns out to be a bit more complex. So it looks essentially like this. So there is a bunch of physical terms inside, but most importantly, there is the amplitude of the wave, and there is the elliptic parameter m coming in. So what this periodicity condition is doing, it's linking the amplitude of the soliton with the elliptic parameter of the solution. So, and it does this in a bijective way, which is shown here. So we have amplitudes depending on m. But since the torus is at the end of the day, it's a physical body, it has a finite size, we can only achieve certain sizes of our waves. And generally in KdV, this is around 30% of the depth of the fluid. So after that, you either become too nonlinear, so the waves start to break. But in our torus, already we cannot, the torus has a finite width, we cannot go above that. And we find around 20% to be our maximal sort of amplitude with respect to the width of the torus. So we are imposing a physical condition on the maximal amplitude we can achieve, and automatically we are imposing a limit on the elliptic parameters we can achieve, which limits the solutions that we can observe on the torus. But what does this mean for the actual hyperbolic secant for the knoidal solution? Well, this means that depending on the torus plate, so we can have, as we saw, we can have something that's essentially hyperbolic secant. This means simply the size of the plate permitted us to have an m that close to 1 that it's described very well by the hyperbolic secant. But the moment we started to decrease the plate size, the periodicity started to take an effect. And here we can see that already here, for example, we cannot even get even close to 1. There is this whole cutoff here for each of the torus widths. We can also consider this in terms of a phase diagram for the 2 different plates from for the 4 centimeter and the 7 centimeter. So here we had something that's quasi hyperbolic second. Quasi, it simply means we put a limit on m. So after m is more larger than 0.999, it's a hyperbolic second. We cannot physically distinguish it from a knoidal solution. Even already, if you simply plot one on top of the other, you cannot tell the difference. And most of all, experimentally, you cannot tell the difference. But if we decrease the plate, we start to see solutions. We start to approach this region here, where we start leaving our condition of hyperbolic second, and we start to see more knoidal sort of solutions that will have a different behavior. And this behavior comes in the form of the velocity, as I showed before. So the velocity also depends on the elliptic parameter m. If m is close to 1 or equal 1, essentially this is 1/2, and we recover the classical KdV straight line case. Everything is well. But the moment m starts being below 1 considerably, we start seeing completely different behavior for the velocity. And this manages to explain well our data. And most importantly, this sort of shows the presence of elevation solitons, which are actually subsonic. So typically KdV doesn't permit this, but the moment you try to start imposing limits on your amplitudes and limits on your m's, you can get elevation solitons which are subsonic. It is also important actually that we are in a periodic domain, because in a straight line case, the knoidal function is a periodic function. So even if m is a bit large, so 0.8, 0.9, it's not still a soliton, it will still be periodic, so still sort of a cosine. But the moment we put it on a circle, we can actually introduce nonlinear modes. So we can have only 1 wave propagating, only 2 waves propagating, and we limit ourselves to the first 2 actually. So it means it's the same as having a cosine plotted onto a circle. In addition to all of this, so we were interested in looking at the periodic inverse scattering transfer. So I will not go into too much details about this. So in KdV, or in general in integrable systems, we have this notion of the inverse scattering transform. And we thought it appropriate, since we are dealing with a periodic case, to implement it for the period in the implement the appropriate inverse scattering transform. So basically the idea is this is a nonlinear Fourier transform. So the Fourier transform gives you simply modes, so gives you a bunch of frequencies for corresponding to different, simply to cosine functions. Here the idea is to sort of go into a more nonlinear approach, where we can decompose the single signal in a way into nonlinear modes, which either can correspond to solitons or knoidal waves or simply pure linear waves. This is putting it very simply. It's a bit more complicated, but idea is we can associate a certain Schrödinger equation to the KdV equation, and from this we can get the appropriate eigenvalues. And these eigenvalues will either correspond to solitons or, on the right here, to radiation. So if we take our signal with only 2 solitons, these are the eigenvalues that will correspond to those solitons, and these are the eigenvalues that will correspond to something that's pure radiation. And actually, the method manages to tell you exactly what are solitons, what are sort of strongly nonlinear but not yet soliton waves, and what is completely linear in your problem. So it is a more sort of overpowered case of a Fourier transform. So now for something completely different, it's we're moving on to wave turbulence. So we saw that the torus has a very rich linear, already in the terms of the linear spectrum, it has a very rich structure. We saw that it's a nonlinear system in the case of KdV. So might as well start considering other nonlinear surface waves, and in this case, in the form of wave turbulence. So can we actually observe wave turbulence in this sort of form, in this sort of system? How does periodicity influence it? How does finite size influence it? What actually happens in terms of wave interactions? So basically, as Guillaume already told you about wave turbulence, I will keep it short. So basically, the idea is we're starting from three-wave, four-wave, and wave interactions, and building up a system of a large amount of random waves, which are cascading energy from larger scales to smaller scales. But in the torus, we started with this, but we came back to this. So instead of forcing it randomly at for a given, I don't know, from a certain to a certain in a certain interval of frequencies, we will just force the torus at a given frequency and see what happens. We will slowly increase the forcing to start to introduce nonlinearities, and simply look at how the torus responds to monochromatic forcing of large amplitude. And what we actually find, so if we do this, see here I plot 3 signals for 3 different forcings. We start off with something that's fairly regular, it's a sine wave. And we get, if we take the spectrogram, we get only background frequency as expected. But the moment we start increasing a bit the forcing, we start to see these 2 additional frequencies appearing in the spectrogram. And if we continue to do this, it starts to fill up. Now, the first thing to consider here is that the sum of these 2 frequencies is equal to the frequency of the sort of the forcing. So we have a mother wave here that is creating 2 daughter waves. And actually, so this is not new. There are multiple names. One is the triadic resonant instability. This is commonly used in internal waves where they observe a similar sort of instability. There's also the name of parametric subharmonic instability. But essentially, they boil down to having one mother wave that is decomposing into 2 daughter waves. But these need to satisfy certain resonant conditions. In this case, it's going to be it's going to be the sum of the frequencies have to match. So 2 daughters give the mother wave, and both in frequency but also in wave number. So if we take our for example, we try to take our gravitocapillary branch. We try to do this. So here I depict the case where we can do this. This is for educational purposes mostly. But so the sort of graphic depiction is we take the dispersion relation, we put it again onto itself, and we get the 3rd wave here in green, which satisfies the resonant conditions here. But actually, for the size of the torus that we are using, this is not possible to do for 3 waves because the dispersion relation is completely convex, and we cannot get at least any non-trivial solutions to this system. More importantly, as we saw, we have a KdV system which is integrable, and actually, at least already in wave turbulence, you can show that KdV systems do not have, even if you have resonant interaction, you can always get rid of those interactions, because since it's integrable, any energy you put into the system is going to end up in solitons, and there's going to be no transfer of energy between different modes. But as we saw in the torus, we have other branches with which we can actually do the same thing. We take our gravity capillary branch and another gravity capillary branch and start to interact, for example, with a sloshing branch. And actually, it turns out that this works. So if you take the Fourier spectrum if you take a space-time measurement and take the Fourier spectrum of a simple monochromatic signal that's forced strongly enough, we see the forcing here and 2 daughter waves here, and which match precisely the resonant conditions I shown you. So what is going on is that we are forcing the system at a frequency which is hitting the sloshing branch, and this sloshing branch is starting to interact with the gravity capillary branch. So we have essentially a 3-wave, 2-branch interaction going on, and this verifies pretty well the resonance. We can do this for multiple frequency, which verifies very well the resonant conditions that we can predict from the dispersion relations I showed you in the beginning. This is also a very good indication that our dispersion relations actually actually depict what's going on in the torus pretty well. So this system can be modeled by amplitude equations. Unfortunately, since I already said having the dispersion relations is pretty difficult analytically or even numerically, the interaction coefficients even more difficult. So for now, we restrain ourselves to some sort of qualitative description. But what is important to notice, if we start to decompose the waves into different amplitudes, so we know the exact frequencies at which we are getting the waves, and we filter them out and get the amplitudes of each wave, we can notice that actually the daughter waves can have an amplitude that is far greater than the mother wave. So there is the mother waves can become very much depleted in energy, and it can transfer a lot of it to the daughter waves. So we actually need to consider the system in its complete nonlinear form, and we cannot make a lot of assumptions on how the amplitudes are related. Is one much larger than the other? It's hard to say. But here it's saying that, well, I mean, you're pretty nonlinear. We can also see if this is actually an instability. So if it consider still the amplitudes of the three waves, we can see that so the mother wave here in yellow appears first, so reasonably because it's the first thing. And once it stabilizes here, we start to see the appearance of the daughter waves. So this is a semi-log graph. So we see that actually exponentially we get the daughter waves appearing, and in the long-term evolution, they stay stationary. So we achieve a stationary state of it, so of the amplitudes, basically because of balance with dissipation. And if we consider the phases of the three waves, we can see that this as well stays constant in time, and the sign is here at 1. So the total phase is plus or minus it's pi over 2. Not plus or minus, but just pi. So these are all sort of preliminary results. So still there's a lot. So sort of to conclude and give you an overview of what we're working on. So this is the three-wave system. Still, it's pretty new and more or less qualitative, and we are still working on it. Basically, the idea is to use this system now to start to see if we can get to a wave turbulent regime. So we have a mechanism that is giving us interaction between modes, and the idea is to see, can we use this to propagate to smaller scales, because the daughter waves, while they are low in frequency, one of the daughter waves always has a larger wave number, so which is sort of an interesting but it remains to be seen. What we saw for the KDV solitons, periodicity matters and curvature matters, but periodicity most of all, which may seem obvious at first, but since at least in hydrodynamics, periodic systems really are not that common, and using them for something like Korteweg-de Vries solitons and such an analysis of such waves is simply not common, and we were not expecting to find this dependence between amplitude and sort of the solution space that we can have. So in general, the torus actually, it has a very rich structure in terms of linear, but it turns out to be highly nonlinear, giving for now, and we hope also in the future, it will give even more interesting results. So thank you.
Thank you very much. Questions?
So when you have the multiple waves, like you have the 3, but then when you see the graph,
Yes.
do you know if it's also perceived?
Yeah, they're secondary waves. We can do the same game. So
it's all resonant interaction.
Yeah. So essentially, what's going on here is that so this one gives these two, and then taking the difference of these two gives this one, and then it needs to find a partner to give again the first one, and this keeps going if we increase the first thing.
on one of the graph, you show that the motor annual amplitude becomes lower by the
Yes.
curve. Could you tell me, because at the time could go approximately the amplitude of the motor is quite low. So, on the energy conservation.
I mean, we are constantly injecting energy. So what's going on is that what's going on is that we are injecting energy, and at some point this the instability develops, and the mother wave is starts to transmitting the injected energy directly to the daughter waves. So essentially, it's almost ignoring the mother, and it's injecting it to the daughters. And this is then balanced also by dissipation.
You're exciting either of those.
We have not tried that yet, but according at least, I think it depends very much which wave you force. So I think you need to start. For example, I tried doing experiments so below the sloshing branch. So the daughter waves for low frequency are always below the sloshing branch. So we can imagine trying to actually the best is to show you here. So this is the sloshing branch. We can try to force here, right, and see if this gets excited. But no, it does not. We simply don't observe the energy going up.
There's no magnitude of expansion.
I mean, the first thing that I used, I tried to vary the forcing a lot and going to sort of extreme ones. So what I find if I do it here, I simply generate harmonics, which become stronger and stronger. But I think that could be related actually to the interaction coefficient, because in a way I think they should be limiting which wave the energy transfers between the waves.
So if you want to go into this wave turbulence picture, is it true that you can't excite only one wave and you're going to force?
Yeah, exactly. It's a bit tricky because, for example, it's the same in internal ways. They use the same argument that this can give, so in a way, turbulence. Essentially, I think what would happen is that also by exciting harmonics, we can have interactions between harmonics, but it's a question if this is actually wave turbulence or not.
But on that question, if you were to drive a very low frequency, I mean, so was also possibly putting in rotation
yes.
as well. The couplings would be much easier. So if you force even a limited spectrum,
yeah.
you would fill in the gap
yeah.
possibly way faster. Are you planning?
Yes, we are definitely. I mean, already putting it in rotation, definitely. And but this is still something we're exploring. So especially in terms of energy cascade from large to smaller scales, we have some results that we're not so sure about them and how they fit into this picture.
Last question. Everyone wants to eat.
On.
You haven't eaten enough yesterday evening. Okay. Well, thank you very much for all of your answers.